Yo, 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 what's up? Today we're going to do problem two. Number of ways to select buildings. Now, oh man, look at that. You see that? Some people ask me, hey bro, how did you get absolute guns like this? And I'll tell you, it's all from Leetcode. I'm telling you right now, if you Leetcode every day, you'll start noticing that you get ripped. And it's really simple. The more you use your brain, the heavier it becomes, full of information. The heavier your brain is, the more weight your body has to support. And the more weight your body has to support, naturally, as a response, your body will produce more muscle. So maybe you do Leetcode to get a six-figure job. Maybe you do Leetcode because you just like solving puzzles. Or maybe you do Leetcode because it's the best workout you could possibly do. Anyways, let's get right into this problem. So problem, we've already read the description. So you are given a zero-index binary string S, which represents the type of buildings along a street, where S of I equals 0 means that the ith building is an office, and S of I equals 1 denotes the ith building is a restaurant. As a city official, you would like to select 3 buildings for random inspection. However, to ensure variety, no 2 consecutive buildings out of the selected buildings can be of the same type. Okay, so if you're given an office, a restaurant, an office, a restaurant, we cannot select the first, third, and fifth buildings because it would form 0, 1, 1, which is not allowed due to having 2 consecutive buildings of the same type. Return the number of valid ways to select three buildings. Okay, only 3 buildings. So it's funny how there's always these problems where like they try to add this layer of like complexity, not so much complexity, but an explanation of what you're doing and why you're doing it. But essentially this problem boils down to fundamentally, given a binary string, right, a string of zeros and ones, how many ways can you pick 3 characters such that it oscillates, right? It switches between ones and zeros, right? Because the only possible strings we can choose here, right? Because we're selecting a binary string, right? And there can't be 2 things of the same type. Meaning, like, you can't have 2 ones in a row or 2 zeros in a row. And as a consequence of that, you can't have 3 zeros in a row because 3 zeros in a row would require 2 zeros in a row, and you can't have that, right? But let's just exhaust all possible length 3 substrings, binary substrings, and then determine if which ones are valid. 1, 2, 3, 4, 5, 6, 7, 8. 0, 0, 1, 1, 0, 0, 1, 1. Right, so these are all the possible length 3 substrings you could even find, right? And we know for sure, like, this one is bad because there's 2 zeros in a row, 2 zeros in a row. This one's bad because there's 2 ones in a row, 2 zeros in a row, 2 ones in a row, 2 ones in a row. Right, so like I was saying, oscillating, right? It has to oscillate. Either it's going to be a string of 0, 1, 0, or it's going to be 1, 0, 1. And you can see that in this solution here, right? 0, 1, 0, 0, 1, 0, 0, 1, 0, 0, 1, 1, 0, 1, 0, 1. Right, so it always has to oscillate between choosing 0 and then choosing 1, then choosing 0, right? So in order to select right, in order to select one character, the previous character you must have chosen is the opposite, right? What I'm saying is kind of an observation, which is in order for me to use a 0, the previous thing I had to use had to be a 1. Right? I guess the only exception is the first character, because the first character you can choose either 0 or 1. Okay. So with that said, I guess maybe that isn't the best observation, but let's just go ahead and look at an example problem and see if we can determine something. I already have an idea, but let's just go ahead and do this for the sake of learning. So S equals 0, 0, 1, 1, 0, 1. Okay. So I guess these things have to be in order. So you have to select buildings in order, right? So the way that this problem works, right, with the buildings is that, you have to select buildings like consecutively, meaning, right, like, so you can't like say, oh, I can get a selection like, you have to choose a subsequence of link 3, right? I can't say that this is a solution like, oh, I'll choose this building and then I'll choose this building and then I'll choose this building and then I'll choose this building, right? So then it's 0, 1, 0. No, this solution would be 0, 0, 1, which is not valid, right? The idea is like you can't choose things out of order. You have to choose buildings consecutively. I choose the 0, then the first, then the last one. I can't like swap their orders, which means, right, we have to find all subsequences of link 3 that meet the condition. Okay. So when we look at this problem, I guess one way you can look at it is say like, all right, well, every subsequence has to be a link 3. So maybe we think of this as a graph. So we see a 0 and we say, okay, that's one solution, possible solution that starts with 0. And then we see another 0. And now when we see a 1, well, there could be a solution that starts with 1, but there could also be a solution where 1 is the second character, right? And I'm talking about, this is the first 0 here and this is the second 0 here, but let's not worry too much about that. And then when we see the third one, okay, when we see the third one, where can it go? Well, it can't go here, right? Because that would make 2 1s. It can't go here. It can't go here, but it could be another new solution. But also, thinking about it again, it could also be a solution to this 0 here. So it could be a solution for both of these. Right now there's another 1 that can be in the second spot. Now when we see another 0, well, look at that. This 0 can go here. It can go here. It can go here. It can go here. And it can go here. And it can be its own solution. Right? And then when we have a final 1, where can that 1 go? Where can it go? The problem is you might feel the urge to say, okay, it can go here, and here, and here, and here, and here. But remember that, 2 of these 1s are the same 1 that got let into. So that doesn't mean that all of these solutions are unique, because some of these 1s are the same. Right? So maybe if we go through this again and we do it a little bit different. I guess the idea is, when you look at this problem, you could also, let's just look at it as a graph. So this previous drawing isn't the clearest, so let's do it again. So this 0 could go to this one, and this 0 could go to this one, right? And then when you have a 1 here, it's the same situation, right? This 0 could go to this one, and this 0 can go to this one. And then when you have a 0, well, this 1 could have made this 0. This 1 could have made this 0. When you have a 1, this 0 could cause this 1. This 0 could come to this 1. This 0 could come to this 1. And this 0 could come to this 1. And then the solution is all link 3 paths in this system, right? Because the only way you can get from one node to the next node is if it's the opposite, right? So you can only go from a 0 to 1 and a 1 to 0, and you'll notice that's an invariant in this graph that I built, right? Because there's edges between vertices where it's from 0 to 1 or from 1 to 0. So how many link 3 paths are there? There's 1, right? This is a different link 3 path. 2, 3, 4, Sorry, it's hard to even see all of them. 5. And then finally, I see the last one. I see it. 6. Right, so there's 6 solutions here because there's 6 link 3 paths within this graph. Right, so I guess a natural solution, which is not great, it would be to build this graph in n squared time, because for each node, you would look at all previous nodes that have links into the node. And then you could build this graph and then run some sort of algorithm like DFS or something and just return all link 3 paths. But that's not optimal. I guess one way you can look at this problem a little bit more efficiently is every time you look at a node, there's some decision that you can make when you look at an individual node. So let's say we had a system already built. Okay. When you see a node 0, that node 0 is an additional path, is a candidate for additional path that starts at 0, right? So there's paths that start with 0, right? There's paths where 0 is the second element. And there's paths where 0 is the last element. Now, so when I have a 0, what I can instead ask is like, okay, when I have a 0, let's just look at zeros as a graph, as a system. How am I going to do this? So there's paths that I've seen so far where they start with 0, where 0 is the second element and 0 is the third element. So I'll create this array like this. Okay. And there's also a path for 1. The same dealio, right? There's a path where 1 is the 0 element, the second element in the path, or the third element in the path. Path that I've seen so far. Okay. And what we'll do is we'll process this string here. So we'll look at S equals 0, 1, 0, 1, 0, 0, 1, 1, 0, 1, right? So when I look at this first node 0, what can I determine from that information? Well, that means that there's a candidate path, right, where 0 is the first element. Does that make sense? Right? There's an additional path. There's a candidate path, a path that could exist later where 0 is the first element. Okay? And there's 0 paths so far we've seen where 0 is the second element. There's 0 paths so far we've seen where 0 is the third element. There's 0 paths where 1 is in it because we haven't even encountered a 1. Now when we look at 0, well, I can't append a 0 to a 0, right? So there's no additional path here. I haven't seen a 1 yet, so these are all 0. But now there's 2 nodes, right? I have 2 cases where 0 is the first path. Right? So now I have 2 cases where 0 is the first path. Now I see a 1. Well, now when I see a 1, that means that there's one case, right? There's one case where 1 is the first path. But now how many cases are there where 1 is the second element in the path? Well, there's 2, right? Because I've seen 2 zeros. So now that means there's 2 such paths in this graph where 1 is the second element, right? So that means that there's 2 such elements in this path where 1 is the second element, right? Because there's this first path we gathered here that starts with 0, and the second path here that starts with 0, and they both go to 1 as the second element, right? Does that make sense? And then there's this single node here, which represents this 1. So we're really adding nodes to this graph, and we're collecting information about paths that could exist in this graph just by summing through like this. And there's 0 nodes where 1 is the third element, right? Because we haven't even had a case where that could occur yet. And this information doesn't change, right? In this iteration, how many nodes are there now where 0 is the first element? Well, there's still 2 cases right here and here. How many nodes are there where 0 is the first element? None yet, right? Because we haven't seen a 1 yet to put the 0 on. In this case, we haven't had a 1 before 0, so this is still 0 and 0. Now we see another 1. So now that we see another 1, where could that 1 go? Well, that 1 could be its own path again. So that means this information changes to 2. And that 1 could also be the second node in the path for the 2 zeros we've seen already. So that means now there's 4 cases, right? There's 4 such cases where 1 is the second node, right? This is the first case, the second case, the third case, and the fourth case. Still 0 here. This information doesn't change because we haven't seen any additional zeros. Might as well cross these off. Now we add another 0. Well, if I add another 0, right? Again, it could be it's a candidate to be the first element in a path. So now we have 3 cases where paths start with 0. It could also be the second element in a path, right? Because it could go from 1 to 0 and 1 to 0. So this becomes 2. And there's also 4 cases where it's the third element in the path, right? Because there's these 2 linked paths, right? That's what this information is. This is the path where 0 is the second element in the path. But there's also 4 linked paths, right? There's this path, 1, 2 path, 3 path, 4 path, 4 unique paths, right? And for a path to be unique, there just has to be 1 edge that's unique, right? And then this information doesn't change because we just processed a 0. And finally, when we look at this last 1, again, this 1 could be its own beginning of a path. So now there's 3 such cases where 1 is the first node. It could also be the second element in a path for how many nodes? Well, it could be the second for this 0. It could be the second node in the path for this 0. And it could also be the second in path for this 0. Right, so that means there's 3 such paths. And then how many paths is it the third node? Well, that would be 2, right? Because there is this path 1, 0, 1 and 1, 0, 1 like that. Right, so there's 2 paths where it's the third node. So that means this becomes, I already did it here, 3, 3, 2, and then this stays the same because we didn't process anything new. So then when we add up this information, well, we're looking for all length 3 paths, right? And there's 4 such paths where it ends with 0. And there's 2 such paths where it ends with 1, and that's 4 plus 2 equals 6, which is a solution. So how did we kind of capture this in a recurrence relationship, right? Well, if I had a value being either 0 or 1, so value is a member of 0 or 1, right? It's just one of these values. It's a set though. Value in 0 or 1. And then in here, the node number. Position, I guess position and path, right? So position would be either 0, 1, or 2. right? Because a node could be in position 0, right? If you have every path that's linked 3 looks like this. So the node could be in this position. It could be in this position, or it could be in this position. So every time you see a node, right, that becomes a candidate for a new path where that's the first node in the path, right? So for every value at position, right, you plus equal 1 to it every time, or not at this position, at position 0, every time you see that value, you add 1, right? Because like, notice every time we saw a 0, we added 1 to this. Let's do that in some color here. Right, every time we saw a 0, we added 1. Right, so that would mean in this solution, this is our, what do we call it? I called it S for some reason, whatever. S of 0, right, because 0 is the value. At 0, right, every time I saw for 0, every time I saw for 0, every time I saw an additional 0, I just added 1 to that system. Every single time I saw a 0, right? And that's the same thing for 1, right? Every time I saw a 1, this got incremented. Okay. Now, when a value, when does a value become the second element in a path? Well, that's just going to be the number of times you've seen the other value as the first element, right? Why did this become 2? This became 2 because there were 2 such cases before I added it, right? There were 2 such cases. That was this system here when we first started, right? There were 2 such cases where 0 was the first element. So that means if I attach this thing, that means there's 2 nodes where 0 is the first. So this additional node means that there'll be 2 paths where 1 is the second. Okay. And that's the same thing here, right? I added another node. So now for this one, I guess I could color it different, right? When I added the node here, that's this node, there were 2 such cases where 0 was the first node. So that means I got an additional 2 such cases where 1 is the second node, right? So where 1 is the second node, so if this was 1, I get an additional 2 such cases where 0 is the first node, right? So if I say value equals 1, right? So S of 1, where 1 is the second node, I add in the number of cases where 1 minus 1 is the first node. So S of 1 plus equal the case where S of 0 is the first node, where 0 is the first node. Okay, and then that's the same, and then the same situation with 3, right? The number of cases where where a value is the third node is you add in, well, how many cases are there where the other value is the second node, right? So I guess these are our 3 main equations, right? We have an equation where every time you see a value, it's a candidate to be the first node in a length 3 path. Every time you see a value, if there's a node of the opposite value, right, then that node's value is sorry, I lost my train of thought because I was looking at myself in the camera just thinking, wow, this probably looks very strange to someone watching. I thought it was funny like 5 minutes ago. It's still funny. Come on. What was I saying? Right, the number of places where a value is the second node is the same as the number of places where the other value is the first node. So if you have 7 cases where 0 is the first node and I encounter a 1, that means there's 7 places where that 1 could go. If I encounter another 1, there's still 7 additional places where the new 1 can go, right? So I keep adding in the number of times that I see the other value. And it's the same game for this, right? So what's the runtime of this? Well, the runtime is n, right? Where n is the length of this binary string array, because I only have to do 3 operations every time I encounter a value, right? I do an operation to see, I do an operation to say, okay, this value is now potentially the first value in a linked 3 path. See how many times this value is the second node in a 3-link path, and how many times this value is the third node in a 3-link path. And then in terms of space, well, this is constant, right? Because this is 3 by 2, so 6 elements. It's constant space. All right. So we'll create that S array, right? So you assume 0, right? Because we don't know. Times 3, right? Because 3 meaning the link 3 path, for blank in range 2, right? Because it can either be 0 or 1. So we have value equals 0, value equals 1 for each value. There's a link 3 array to correspond to what position that node is in the path. All right, and then we just look at each node. So we look at each node, we'll call it C in S. Now what I'm going to do is actually convert the character to an integer, just to make it a little easier to handle because it's given as a string, right? Sorry, Matt, convert it, okay. So that means S of the character, right? Where the character, well, we'll call it value because I kept calling it value in this thing. So S of value at 0 plus equal 1, right? Because that means now there's a new case, again, where this node's value is the first character in the string, in the path. And then the value at 1, well, how many times is it the second node in the path? Well, that's the same as the number of times the other character, if you do 1 minus value, you can make that work, is the first node in the path. And how many times is it the second node in the path? Well, that's the same thing as the third node in the path, the same thing as the other node being the first node in the path. And then at the end, you just return the sum of -1, or we'll call it 2. Or we'll just make this a little cleaner. Value 2 for value in range 2. Right, so for 0 and 1. Right, because 2 is the number of times this node's value is the third member in the path, right? And we want a link 3 path. So we just look at each value, 0 and 1, and we add that up and return it. Sorry, I had 2 different ideas, and I wanted to make one more clear, and then Cool. So let's go ahead and submit that. Made it big so you can see how excited I am. Ah! Bam, son! And then last thing we'll do. Now, I know everyone's going to be mad when I do this, but it's very important that your solutions are short and they make no sense. Okay? So there'll be 3 things. This will also equal itself plus this. And then finally, this will equal itself plus this. In Mahood, we call that a 3-line solution. Yeah. What? All right, guys. You have a good day now. Peace.